Hey everybody. You know, when we started in chapter 1 and had equations, those things you loved from algebra, a lot of people told me they were pretty excited. Once we started doing inequalities and graphing things, wow, yeah, the doors really came off there. Then we got into this chapter 3 where we had systems of equations, like more than one line, and we're figuring out where they intersect. I've had so many people come up to me and say, Walsh, is there any extra I could do? Is there like another book I could take home that has more problems in it? This stuff's fun. I just wish it was more complex. Well, to those of you who've been looking for something even more fun, I've got what you ordered right here. 3 variable, 3 equation systems. You know, you thought one line was fun. Then you met 2 lines, and 2 lines got even more fun, but 3 lines? Oh my gosh. It's like you've gone to heaven, I understand. You know, when we talked about 2 lines, we had 2 variables, so you needed 2 number lines in order to graph those variables. In order to graph 3 lines with 3 variables, you need a third dimension. So you would have what we would call the z-axis, kind of going off into space, if you can imagine it like that. We would still have the y-axis, and you still have your x-axis. And so there's some point out in this 3-dimensional plane that all 3 of these lines would intersect at one point. All 3 lines intersecting at one point. Theoretically, they might not match up. But instead of our answer being a 2-variable coordinate, like x, y, our answer to this is going to be a 3-variable coordinate like x, y, z. Now, figuring this out by graphing is going to be really tricky, especially if you're trying to do it on 2-dimensional paper. Luckily, solving it algebraically isn't as complex. Now, because we have 2 methods, we have the substitution method and the elimination method, either is applicable here. But I find, in my experience, that students tend to prefer the elimination method when it comes to solving these systems. So I'm going to show you how that would work. Step 1, we need to eliminate either the x, the y, or the z from all of these equations. You could eliminate the x's pretty easily. If this x was matching, if the blue equation was matching the red equation, I could just make this 2, and the x's would match up. If I was matching the blue and the orange, I could make 3x and 3x by multiplying by 3. That'd be pretty simple. I could match up the y's, wouldn't be too hard, but trying to get the 2 and the 3 to match, or you could have the negative match with positive 3y, the negative match with the positive 2y. That's not so bad either. Or even we could match the z's. This is a problem where there isn't one that really stands out as the easiest thing. Me personally, I would eliminate the z's, but since we're dealing with a negative and a positive, I know sometimes that throws a few of you, so I'll just match the x's. Let's say I wanted to use the blue equation and the red equation, and I wanted to match x's. Either I could divide everything in the red equation by 2, but then we'd have a fraction here. Nobody loves fractions. I love fractions, but nobody loves fractions. So we're going to multiply the entire blue equation by 2. The result would be 2x plus 4y minus 2z equals 4. Now I'm going to write that right underneath. Actually, I'm now going to grab the red pen, and I'm going to write the red line immediately underneath that. 2x minus y plus 2z, again I'm just recording the red line, equals 6. Now, fun fact, if I were to add these 2 equations together, the z's would eliminate, and instinctually that's what I would do in this problem. But I'm going to commit to always subtracting here for you, so I don't mix up those of you that are just barely hanging on. We got 2x minus 2x. That would cancel out our x's. Here's the tricky step. 4 minus negative 1 minus negative 1 is 5y. And then negative 2 minus positive 2. In other words, I'm already negative, and I'm taking away 2 more, is negative 4z. And 4 minus 6 is negative 2. Now that got us closer to an answer. That's for sure closer to an answer. But we still have an equation with 2 variables, so we don't know what y and z equal in this instance. There are numerous things that y and z could equal so that it worked out to negative 2. We need to figure out which one of those solutions also works when we include the orange line in the mix. So to include the orange line, I'm again going to manipulate the blue line. This time I'm going to take that blue line, which was x plus 2y minus z equals 2, and I'm going to multiply that by 3 this time. The result will give me 3x's, which will match the 3x's that were in the orange one. Alright, so when I multiply, again, times every single term, I'm going to get 3x plus 6y minus 3z equals 6. 3, 6, negative 3, 6. Yep. Now I'm going to go to my orange line. I'm going to record this line immediately underneath my new manipulated blue line. 3x plus 3y minus 2z equals 3. And when I subtract here, my x's eliminate. 6y minus 3y is 3y. And negative 3z, take away negative 2z, negative 3 minus a negative 2. I had negative 3. I'm taking away 2 of those negatives. That leaves me with a negative still. Negative 3 minus negative 2 is negative 1. Finally, 6 minus 3 is 3. Again, that gets us closer to an answer, but it doesn't get us all the way there. But we have one equation that has 2 variables. We have a second equation that has 2 variables. So what could we do? Exactly, Adam. We could match up the letters and eliminate, or we could solve, for instance, for z and substitute. Since we've already done mostly elimination, and since we did elimination throughout this problem, I'm just going to stick with elimination. If I wanted to match up these 2 black lines now, we could either make it so the y's are 15, or we could leave this one alone and manipulate this one so the z's matched up. What could I multiply that by in order to match them up? Well, I'm at negative 1 here, negative 4 here. If I multiply everything by 4, they're going to match up. But again, that's everything. So 4 times 3y is 12y. 4 times negative 1z is negative 4z. And 4 times 3 is 12. I'm going to subtract one last time here. 5 minus 12 is negative 7y. Negative 4z, take away 4z, minus negative 4z. There's no more z's. And negative 2 minus 12 more is negative 14. And if I divide both sides by negative 7, I get y equals positive 2. Whew, that was a lot of work, yeah? Don't get disappointed, there's still more to do. Remember when we had 2 variable systems, we would solve for y, but we didn't know the x value. We had to substitute this back into an equation to figure out x. We're going to have to substitute this back in to get both x and y. So I'm going to look for any true equation on my paper, which at this point I hope every equation I've written has been true, otherwise we're in for some trouble. And I'm going to look at one of the ones that only had 2 variables. The easier one was the one that said 3y minus z equals 3. By easier, I mean it has the lowest coefficients, the smallest numbers. And if I plug in this 2 here, I'm going to be able to solve for z. Right? I'm going to say 3 times my y value minus z equals 3. But instead of writing y, I'm going to take what y was equal to, the 2. That gets me 6 minus z equals 3. Now logically, that means if I take some number away from 6, I get 3. Some of you might know what it is already. But algebraically, I'll subtract 6 from both sides and get that negative z equals negative 3. Or simply that positive z equals positive 3. I'm now 2/3 of the way to my answer. My final answer is going to be something, comma 2, comma 3. My y value is 2. My z value is 3. I just need to figure out my x value. What's that call for? One last substitution. Go back to your original equations and ask yourself which one is the simplest, which one has the smallest coefficients. I'm going to vote for blue. Blue was pretty straightforward, so I'm going to record blue. down at the bottom, you can trust me, I'm doing this off camera at the moment. I'll show you in 1 second. Alright, I'm taking blue, and I'm going to write blue right down here. X plus 2y minus z equals 2. And I'm going to write this, and I'm going to insert the values 2 and 3. I'm going to substitute them in for y and z. So I'm going to get x stays as is, plus 2y minus z equals 2. But I'm going to insert the values that I know. Y is 2, z is 3. That gives me x, 2 times 2, plus 4, minus 3 equals 2. I'm going to combine the 4 and negative 3. That gives me x plus 1 equals 2. Subtracting 1 from both sides, I get x equals 1. My actual final answer is this. X is 1, y is 2, z is 3, and you can write that as what we call an ordered triplet. 1, 2, 3. Just goes in alphabetical order. X, y, z. If your variables were a, b, and c, they would go a, b, c. As long as it matches the alphabetical order, you can put it as an ordered triplet. Told you that was going to be fun. And just 11.5 minutes of your life.